In this project, we want to see how A/B testing works in a real business condition and how it helps teams make better decisions based on the data. The goal is to understand how experimentation can reduce guesswork and support confident business decisions. Our product is a subscription-based digital product. It offers a free basic plan, and users can upgrade to a premium plan to access more advanced features. Historical data shows that many free users visit the pricing page, but only a small percentage of them actually upgrade to premium. These behaviors suggest that there may be a friction or lack of clarity on the pricing page. Users might not fully understand the value of the premium plan, or they may not feel confident enough to make a purchase decision. The low conversion rate from free to premium creates several business problems. First, it reduces subscription revenue. Second, it lowers users' lifetime value because fewer users become paying customers. It means that a lot of traffic to the pricing page is wasted without generating value. The product team believes that the current pricing page does not clearly explain the value of the premium plan and does not guide users toward a quick and confident purchase decision. The objective of this experiment is to test whether a redesigned pricing page can increase the free to premium conversion rate. At the same time, we want to make sure this improvement does not negatively affect user experience or other important business metrics. More specifically, we want to answer this question. Do the changes made the pricing page lead to a statistically significant increase in conversion compared to the current version or not? A/B testing is the best method for this problem because the change happens at the specific point of funnel, which is the pricing page. We also want to measure the causal impact of this change on the user behavior. By choosing A/B testing, we can fairly compare the current version or control with the new version or treatment and make decisions based on reliable data instead of assumptions. At the end of the experiment, we expect to make one of these three decisions. If we see a strong and statistically significant improvement, we will launch the new pricing page. If the results are positive but not strong enough, we will iterate and improve the design further. If the treatment shows no improvement or creates negative effects, we will roll back the change. In this experiment, control A, group A, is a current pricing page and serves as the baseline. And treatment, or group B, is the redesigned pricing page with changes in how plans are presented and how the call to action button is displayed. To keep the experiment clean and unbiased, several elements remain unchanged. Prices stay the same, plan features don't change, and the checkout and payment flow is not modified. User eligibility also stays the same. This ensures that any observed difference comes only from the changes to the pricing page. A user is considered exposed when they visit the pricing page and are assigned to either variant A or B. We record a timestamp of the first time each user sees the pricing page. This timestamp is used as a starting point of analysis. The experiment population includes users who are on a free plan, visit the pricing page during the experiment window, and are exposed for the first time to either control or treatment. Only these users are included in the analysis. If we include all free users in the experiments, even those who never visit the pricing page, the conversion rate becomes artificially low. This weakens the treatment effects and increases the required sample size without adding any value. If we include only users who converted or highly active users, selection bias is introduced. This would make the results unreliable and not representative of the overall free users population. Exposure time is defined as the first time a user views the pricing page. At that moment, the user is assigned to control or treatment. A 7-day conversion window starts immediately after exposure. If a user visits the pricing page multiple times, only the first exposure is counted. If a user downgrades back to free, they remain in their original group. If a user switches devices, the site variant remains the same using the persistent user ID. The primary metric is the free to premium conversion rate. It is defined as a percentage of eligible users who upgrade to premium within 7 days after viewing the pricing page. The denominator includes all exposed free users assigned to either variant. The numerator includes users who successfully upgraded within the conversion window. Secondary metrics are not the main business goal, but they help explain why the experiment succeeded or failed. They answer the question of how user behaved during the funnel. CTR measures how many users viewed the pricing page and clicked the upgrade button. If conversion increases but CTR doesn't change, the improvement likely comes from later steps. And if CTR increases but conversion doesn't, it suggests friction after clicking the CTR. Checkout start rate measures how many users start checkout process after clicking the CTA. This helps us understand whether users click the button with a real purchase intent or just curiosity. Refund rate measures how many users upgrade and request a refund within 14 days. A high refund rate suggests that users upgraded with incorrect expectations or that pricing page oversold the product. Even if conversion rate increases, a high refund rate can invalidate the experiment results. Early churn rate measures how many premium users cancel within 30 days. High conversion combined with high churn indicates artificial growth and poor user experience. A hypothesis clearly defines what we are testing and how we make decisions. Without hypothesis, an A/B testing becomes just a comparison of numbers with no clear meaning. The null hypothesis is the pricing page changes have no effect on the conversion rates. Any observed difference is due to a random chance. An alternate hypothesis is the redesigned pricing page increases the free to premium conversion rate. The significance level represents the risk of the false positive. We use alpha 0.05. The statistical power represents the chance of detecting a real improvement. We target 80% power. MDE, or minimum detectable effect, is the smallest conversion improvement that is both meaningful for the business and detectable for the experiment. In this project, a 1 or 2% uplift is considered realistic and valuable. The experiment uses 3 tables: assignments, events, and subscriptions. Together, they tracked exposure, user behavior, conversion, refunds, and churn. Sanity checks ensures the experiment was implemented correctly and the data is reliable. Here, we should verify that users are split evenly between control and treatment. Here, we should check that users enter both variants evenly over the time. Here, we should make sure each user must see only one variant, A or B. All events must occur after assignments and follow the correct order. We verify that pricing views, CTA clicks, and checkout events are properly logged. We check for duplicate users and missing critical events fields. First, we calculate the conversion rate for both control and treatment groups. We observe that the conversion rate in treatment group is higher than the control group. However, observing the higher conversion rate is not enough. We must test whether this difference is real or could have happened only by chance. To do this, we use one-tailed two-proportion z-test. Because our alternative hypothesis expects the treatment to perform better than control. We compare the p-value with the significance level alpha 0.05. In this experiment, the p-value is greater than alpha. Therefore, we fail to reject the null hypothesis. This means, although the conversion rate increased, we don't have the strong statistical evidence to say that the new pricing page truly caused this improvement. Guardrail metrics helps us make sure that even if conversion improves, we are not harming user experience or business quality. For refund rate, we used two-sided hypothesis tests because we want to detect any change, whether increase or decrease. We again compared the p-value with alpha. In this case, the p-value is less than 0.05, so we reject the null hypothesis and we accept the type 1 error if it happens. This means that the refund rate in treatment group is statistically different from the control group. Since the refund rate increased, this suggests that users upgraded with incorrect expectations. Even if conversion improves, a statistically significant increase in refund is a negative signal and weakens the business value of experiments. We apply the same two-side hypothesis only for early chain rate. The p-value is greater than 0.05, so we fail to reject the null hypothesis. This means that the observed increase in churn is not statistically significant. However, even a directional increase in churn is still a warning signal when combined with higher refunds. CTA-CTR helps us understand whether the pricing page itself increased user intent. We test whether CTR is different between control and treatment using the two-side test. The p-value is greater than 0.05, so we fail to reject the null hypothesis. This means there is no statistically significant change in CTR. Therefore, the pricing page did not increase user intent at the click level. So finally, if we want to give the managers as a decision-making suggestion, we can say, although the treatment showed a directional increase in conversion, this improvement is not statistically significant. At the same time, refund rate increased in a statistically significant way. This combination suggests that the new pricing page may be encouraging more users to upgrade, but with misaligned expectations. So as a final decision, based on the primary metric and guardrail metrics, the correct decision is iterate and not launch it. The pricing page should be improved to better align communicated value with the actual product experience before running another experiment. This project shows how A/B testing helps business make decisions based on the evidence and data, instead of just relying on assumptions. All the analysis code and project files are available on my GitHub. The GitHub link is provided at the bottom of the video. I hope you enjoyed this project, and thanks for watching.